The purpose of this video is to study the Cauchy criterion, and the Cauchy criterion represents a way of identifying if a sequence is convergent without actually knowing the value of the limits in advance and without having information about its monotonicity. So the plan is as follows. First, we will define what a Cauchy sequence is. We'll look at some examples. And later on, we'll look at a Cauchy criteria and we'll in fact prove that a sequence is in fact Cauchy if and only if it is convergent. So we'll say that a sequence AN is Cauchy. So a sequence is a Cauchy sequence if for every epsilon there exists a natural number n such that if m and n natural numbers are greater than n, then the distance between an and am is no more than epsilon. So in other words, if you have a Cauchy sequence, if somehow there is a point inside the tail of the sequence so that past that point, the distance between any element inside that tail is no more than some prescribed value epsilon. Let us in fact look at an example. So we would like to consider the sequence an, which is 1 over n, and we would like to show that this sequence is a Cauchy sequence. So first, let us discuss a little bit what we need to prove here. We need to prove that, so here we want to show that for every epsilon greater than 0, there exists some natural number n such that if m and n are bigger than capital N, then the distance between an and am, which is here basically 1 over n minus 1 over m, is no more than epsilon. Now, let us look at this quantity here that we are trying to estimate. So if we look at this quantity, so we note that the distance between 1 over n and 1 over m is less or equal to 1 over n plus 1 over m, and this is by triangle inequality. But this is precisely 1 over n plus 1 over m. Now, in order to make this, if we want to make all of this less than epsilon, it suffices to make this less than 1 over epsilon, and it suffices to make this less than epsilon over 2 and this less than epsilon over 2, right? So we want to find n and m large enough so that 1 over n is less than epsilon over 2 and 1 over m is less than epsilon over 2. But this really means that we just need to make sure that both n and m are bigger than 2 over epsilon, right? So to make this estimation here, it is enough to choose n and m to be bigger than 2 over epsilon. So for us here, we will need to choose n to be at least 2 over epsilon, right? So this is our discussion. Okay, this is just the scrap work. We haven't written a proof yet. Now, how do we write the proof? So here's the formal proof. Let epsilon be a positive number, period. By the Archimedean property, we choose n so that n is bigger than 2 over epsilon. right? And we can do that because we choose n in a natural number so that this happens. We can do that because the Archimedean property tells us that no matter how big a number is, we can find a natural number bigger than it. Now, next, suppose that little n is bigger than big N, then 1 over n will be less than epsilon over 2, and 1 over m is also less than epsilon over 2, right? In fact, here's a better wording. Oops, sorry about that. Here's a better wording instead. Assuming that little n and little m are bigger than capital N, we have, as such, the distance between 1 over n and 1 over m is going to be less than this plus this by triangle inequality, which is which is less or equal to epsilon over 2 plus epsilon over 2, which is epsilon. And this gives us what we want. So we can then conclude that that the sequence 1 over n is indeed a Cauchy sequence. Right. In this exercise, we will prove that the sequence given by 1 plus negative 1 power n is actually not a Cauchy sequence. Let us have some discussion before we move forward. So here we need to show that an is not a Cauchy sequence. What does that mean? Writing down the negation of Cauchy sequence, that means, in other words, if we use the negation of this definition here, you can actually pause and try to negate for yourself. But if you use the negation, you will see that what we really want to show is that we want to show that there exists some epsilon which is greater than 0, such that for every natural number n, there exists little m and little n bigger than n, such that the distance between an and am is greater or equal to epsilon. This is what we want to show. Now, notice that the sequence an itself is really, if you try to compute the term of the sequence, if n is 1, you get 0. If n is 2, you get 2. And then it alternates. 0, 2, 0, 2, 0, 2, and so on. It keeps going in that fashion indefinitely. Okay. Now, note that given n and m, which are natural numbers, if you compute the distance between an and am, we'll get 1 plus negative 1 power n minus 1 minus negative 1 power m. And that, of course, is negative 1 power n minus negative 1 power m. So, in fact, this sets for every natural number n and m, you will agree that whatever this number is, it's in between. It's either 0 or 2, nothing else. Let me explain myself. Suppose that both n and m are even. Right, so you get 1 minus 1. which is 0. Suppose n is even and m is odd. In that case, you'll get what, 1 here, and then minus 1, so that'll be 2, right? And so on. So you can check for all possibilities that we have that regardless of which combination of n and m that you take, that quantity is going to be either 0 or 2. So in fact, if n is even and you choose m to be n plus 1, then what you're going to get is this. Which is 1 plus 1, which is 2. And on the other way, otherwise, if n is odd and m is, say, n plus 1, then you get that negative 1 power n minus negative 1 power m is going to be negative 1 minus 1, which is of course 2, right? So now, by selecting, if we decide to select, so by selecting epsilon to be 1, no matter how large big N is, we can find little n and little m bigger than n, so that the distance between 1 over n and 1 over n plus 1, so this is really is just, notice that this here is just m, right? We choose m to be n plus 1. This will be 2, which is bigger than 1. So in other words, we cannot make the distance between consecutive terms arbitrarily small, right? So that gives us exactly what we want, which is to show that there exists some epsilon. Our epsilon that we found here is 1, so that no matter what n, how big n is, there exists m and n, so that the distance between m and n and am is bigger than 1. All right. So this is our discussion or our scrap work. Now that we have organized our thoughts, we can write the proof. Okay. So to write the proof writes itself after the scrap work, as you can see. We say let epsilon be 1 given any natural number n. Note that the distance between these two quantities is always going to be 2, right? And okay, on an exam, you really want to substantiate this a little bit by using the argument provided here in your scrap work. But okay, so in the interest of time here, I'm going to keep it short. And this is greater than 1. As a result, the sequence 1 plus negative 1 power n, natural number, is not a Cauchy sequence. And this. Now we will show that any Cauchy sequence is actually necessarily bounded. Okay, so for the proof, let an be a Cauchy sequence. Now I'm going to fix epsilon, which is 1. And because the sequence is Cauchy, we can then choose n, which is a natural number, so that the distance between an and am, let me use, in fact, the distance between an and an is less than 1 whenever little n is bigger than capital N, right? That's given to us by the definition of what it means to be a Cauchy sequence. If you don't really understand that, feel free to pause the video and try to work this out for yourself. Now, observe that the distance between an and an, this statement is in fact equivalent to the statement -1 is less than an, and it's an which is less than 1. And of course, this really means that an is in the open set a capital N minus 1, a capital N plus 1. This means that the sets containing elements of the type an, where n is strictly bigger than capital N, is bounded. So the tail, we're simply saying here that the tail of the sequence is bounded. Is a bounded set. Now, moving forward, in fact, we know here that an upper bound is 1 plus an, right? So in fact, 1 plus an is an upper bound for these sets. But if you look at this, the head of our sequence, this is also a bounded set, since it's finite. Since it is a finite set, right? You can just count the number of elements and pick the largest. That's really what this is. So now, because every element of the sequence is a union of this set here together with this set, okay? Because it has to be a union, then the entire sets containing, this is what I'm trying to say. So in light of these observations, the set an, where n is now containing everything, is also bounded. Do you see this? I would like here to challenge you to sit down and actually write a short proof for this fact, that if you have two sets which are bounded, then the union must be bounded. If you can prove that, then you have proved exactly the claim. Okay, now we will prove that a sequence is convergent if and only if it is actually Cauchy. So in other words, the condition of convergence can be replaced by the condition of Cauchy. Let's write a proof. Assume an is a convergent sequence. Moreover, So in other words, and okay, so let A be a real number such that the limit of an as n is approaching infinity is equal to A. Observe that for any natural number n, one have that the distance between an and am is this is a nice trick, is an minus am minus a plus a, right? So notice that here I've just rewritten 0, right? This thing here is just 0, okay? But this is less or equal to, in fact, before that, I would say this is precisely an minus a plus negative am plus a, which is of course less or equal to an minus a plus am minus a. Notice that this is due, this inequality here is due to the triangle inequality, right? This is by the triangle inequality, okay? All right. So this is by the triangle inequality. Triangle. Now, to make the distance between an and am less than epsilon, it suffices to make the distance between an and a less than epsilon over 2, and the distance between am and a less than epsilon over 2, okay? Now, since we have assumed that the sequence is Cauchy, so by assumption, is convergent, by assumption, there exists a natural number n, of course, which depends on your choice of epsilon. Actually, so I forgot to say, so fixing epsilon, which is a positive number, by assumption, we can choose some number n, some natural number n, such that the distance between al and a is less than epsilon over 2 whenever little l is bigger than n. So assuming that n and m are natural numbers such that n and m are bigger than n, it follows that it follows that the distance between an and a is less than epsilon over 2. In fact, let me just write all of it at the same time. Plus am minus a is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. Therefore, an is a Cauchy sequence. Okay, so this gives us half of the proof, right? We have proved that if a sequence is convergent, then it has to be Cauchy. Now we need to show that if a sequence is Cauchy, then it has to be convergent. For the converse, Let us assume that an is a Cauchy sequence. From our previous results, we know that an has to be bounded. Is bounded. Okay? So now, by the Bolzano-Weierstrass theorem, an has a convergence subsequence which I will call ANK. So let A be some real number such that the limit as n is approaching infinity of ANK is equal to A. We will show that this sequence has to be convergent as well. Okay? I'm sorry, we'll show that AN instead has to also be convergent and has to converge to A as well. So that's our aim. Okay, so let epsilon be a fixed positive number. We choose then n, which is a natural number, so that the distance between ANK and A is less than epsilon over 2, provided that K is bigger than N. And since AN is Cauchy, there exists M, which is a natural number depending on epsilon, such that if n and m greater than m, then the distance between an and am is less than epsilon over 2. Okay, now assume that little n is actually bigger than the maximum of n and m. So since nk is greater or equal to k, we have proved this by induction before, but if you don't remember, pause the video and check. Okay, prove it for yourself. Since nk is bigger than, we also have that nk is bigger than k for every natural number k. So put k instead here. Then we'll have ak minus a. This will be ak minus a minus ank plus ank. So we rearrange things a little bit and we'll get, again here, it's the same old trick, rewriting 0 in a clever way. So we get ak minus a minus ank plus so I have here ak minus a. I want to say here, I'm sorry, so here we'll have ak minus ank. I mean, okay, plus A and K minus A. There you go. And then by triangle inequality, let me call this thing here star. Star is now less or equal to AK minus ANK plus ANK minus A. Now, because K is bigger than N, right? And because NK is bigger than K, then this thing here is going to be bigger than epsilon over 2. And because ANK is convergent to A, and we've chosen K to be bigger than both N and M, first converge to epsilon, the first is less than epsilon over 2, and the second also. So by adding these two together, we get, of course, epsilon. And that gives us, so we can now conclude that this sequence is convergent, and it's also convergent to A. So we have proved that a Cauchy sequence must be convergent. So in summary, we've proved that a sequence is Cauchy if and only if it is convergent. The following harmonic series. You may have seen this series before in calculus 2. It's of this form here. Summation of 1 over K when K is going from 0 to infinity. Okay. So I don't want to call this A. It's this. Okay. So what we want to show here is that the partial sum, the sequence obtained by taking the partial sum of the harmonic series is actually divergent. So that means that if you construct the following sequence, 1 plus half plus 1/3 all the way to 1 over n, that sequence has to be divergent. Okay, so how does this work? Well, for this is actually enough to show that the sequence is not Cauchy. Okay, because to be Cauchy is to be convergent. So let's AN be 1 plus 1/2 all the way till 1 over n, and a 2n, okay, the sum of the first, okay, 2n. Then if we consider a2n minus an, then what do we get? We get 1 plus 1/2 plus that plus 1 n plus 1 over n plus 1 plus that all the way till 1 over 2n minus 1 plus 1/2 plus that plus 1 over n. Now notice that this and these are the exact same thing. So they'll cancel each other out. So you're left with 1 over n plus 1 plus that plus 1 over 2n. Correct? Well, now we have n many of these, right? We have n many of these things, but each one of them is at least 2n. Why? Because 2n is bigger than n plus 1. Bigger or equal to n plus 1. So this will be greater or equal to 1 plus 1 over 2n all the way till again 1 over 2n. So here we are adding 1 over 2n n many times. So this means that we have n times 1 over 2n. That will be precisely 1/2. So in other words, no matter how big n is, if you take the difference between a2n and an, you cannot make it less than 1/2, right? So thus, for epsilon being equal to 1/2, for any I want to say given any natural number n, we have that a2n minus an is greater or equal to half. So the sequence is not convergent. This an is not Cauchy, is not Cauchy. That is, it must be thus it is divergent. And this completes this this example. Let us turn to another example here. This is a sequence which is defined recursively. A1 is 1, A2 is 2, but AN is the average of the preceding two terms, AN minus 1 plus AN minus 2 over 2. Okay. For n bigger than 3 or equal to 3. Now, for this here, there's some scrap work which needs to be done before the proof is presented. But I will skip the scrap work and just present you of the idea that will work here. And what I want to do, I claim that for any natural number n, an plus 1 minus an is equal to 1 over 2 power n minus 1. And we'll prove this by induction. Okay? So indeed, okay, I guess we'll say proceeding by induction, we verify that when n is 1, then an plus 1 minus an, this quantity here is going to be a2 minus a1, which is 2 minus 1, which is 1. Right? Which is clearly 1 over 2 power 1 minus 1. Okay. All right. So, I mean, the one way to guess this general formula would have been to, plot a bunch of, to compute a bunch of terms and make a conjecture, right? And then verify the conjecture through induction. Now, next, let us suppose that ak plus 1 minus ak is equal to 1 over 2 power k minus 1 for some natural number k. Then, if you consider ak plus 2 minus ak plus 1, we'll get, okay, by using again the recursive definition, so ak plus 2 is going to be, of course, ak plus 1 plus ak over 2 minus ak plus 1, which is ak minus ak plus 1 over 2, which, now by the inductive hypothesis, this will be clearly 1/2 times 1 over 2 power k minus 1, which is of course 1 over 2 power k minus 1 plus 1, which is 1 over 2k. Okay, so that gives us exactly what we want. Now, for any natural number p, let me make a little bit of space here. So moving forward, for any natural number p, note that an plus p minus an is going to be an plus p minus an plus p minus 1 plus an plus p minus 1 minus an plus p minus 2 plus dot 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 plus an plus 1 minus an, which is less or equal to an plus p minus an plus p minus 1 plus an plus p minus 1 minus an plus p minus 2, and you keep going this fashion until an plus 1 minus an. And this is less or equal to 1 over 2n plus p plus 2 plus 1 over 2n plus p plus minus 3 plus dot 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 plus 1 over, of course, 2n minus 1. Now we can factor 1 over 2n minus 1 out, and that will give us 1 over 2p minus 1 plus dot 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 plus half plus 1, which is 1 over 2n minus 1 times the summation k is going from 0 all the way till infinity of 1 over 2k. The point being that this is a partial sum, right? And this is the full sum. So, of course, this will have to be less. It's supposed to be less. It has to be less than that one. Okay. But I would like you to verify that, in fact, this is actually going to be 2. The sum, this infinite sum, is going to be 2. So we're left with 2 over 2 power n minus 1. Okay, so now let's epsilon be a positive number. We can find n sufficiently large so that, of course, 2 over 2 power n minus 1 is less than epsilon. So the idea is to notice that 2 over 2 power n minus 1 is actually just 1 over 2 power n minus 2. And I would like you to check. Okay, I know I'm leaving a lot of holes in the proof, so but it's for you. Those holes are for you to, the gaps are for you to fill. So check that indeed that's the case, that this is less than 10 over n. And for, okay, so thus for little n bigger than 10 over epsilon, we have that the distance between an plus p and an is in fact less or equal to 1 over 2n minus 2, which is less or equal to 10 over n. And because n is bigger than 10 over epsilon, this can be made less than epsilon, proving that the sequence is in fact Cauchy, and because it's Cauchy, then it's necessarily convergent.